Welcome to lecture number 49 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we have done in the previous lecture. So, in the previous lecture, we reviewed some of the concepts of geometric nonlinear analysis that we have introduced you in the introduction chapter. Okay. And then we have derived the geometric stiffness matrix Kg for a truss element using the principle of virtual work. Okay. So, in this lecture, what we will do, we will study a physically meaningful derivation. In other words, try to understand the geometric stiffness matrix for a truss element, okay, and then follow the same procedure to derive the geometric stiffness matrix for a beam column element, okay, and then we will study the second order nonlinear analysis procedure, okay. We will also solve some examples using hand calculation as well as using OpenCS. So, with that, let us get started. So, let us first do a physically meaningful derivation of the geometric stiffness matrix for a truss element. So, consider that this truss element is in local coordinates. Okay. So, capital P1, capital P2, P3, P4 are the element end forces, okay, and this element has an axial force N which is tensile taken to be positive, and we call this often a P delta strut. Okay. So, this internal axial force N is in equilibrium with the element end forces P1, P2, P3, P4, right. So, P1 is shown in the positive direction and I have a tensile axial force which is like this. So, that means this P1 must be minus N, whereas P3 is N and P2, P4 are both 0. So, this internal force is in equilibrium with the element end forces. Let us assume that this truss element has no axial stiffness, okay. And as I said, this is stated here that N is in equilibrium with the element end forces, right. So, what we want to derive the geometric stiffness matrix Kg, and to do that what we will do, we will impose vanishingly small displacements and calculate end forces or element end forces required for equilibrium in displaced or deformed configuration. So, basically if I write what I am trying to do, I am trying to develop a relationship like this. So, dP is the incremental element end force vector is equal to a matrix multiplied by d little p. Okay. So, here this is 4 cross 1 and this is also 4 cross 1. So, this matrix must be 4 cross 4 and this is the geometric stiffness matrix of the element in local coordinates, right. Now, to derive the first column of this stiffness matrix, what we shall do, if I write dP is equal to dP1, dP2, dP3 and dP4, and these are all lowercase p because we use lowercase to indicate the displacements at the element ends, right. So, if I impose only dP1 and keep all the other 3 0, then what I get? I will get some forces. So, those forces will be the first column of my stiffness matrix. Similarly, I will impose dP2 is some non-zero value, while keeping other 3 0, I will get the second column. Similarly, dP3 some non-zero, dP1, 2 and 4 0, and I will get the third column, and similarly the last column. Okay. Now, since the axial stiffness of the element is assumed to be 0, okay, so the axial force in the bar does not change even when the bar is deformed axially. Okay. That is an assumption that we are making, and we will see what kind of geometric stiffness matrix we get out of this. Okay. So, to get the first column of the Kg, we impose dP1 only, okay, and what do I get? So, if I impose dP1, so this is deformed axially, okay. So, now this force earlier was P1, now I am saying this is P1 plus d capital P1, this is P3 plus D capital P3, and this is, you can write P2 plus D capital P2, but doesn't matter, this is going to be 0, this is going to be 0 anyway. And since I said that this bar or the P delta strut has no axial stiffness, even if I impose this, there won't be any change in the, or it will not offer any resistance, hence this is going to be 0. So, dP1 equal to dP2 equal to dP3 equal to dP4 is equal to 0. All of these forces, the change in the element end forces is equal to 0 when I apply the axial deformation dP1. So, if I write it in a matrix form, dP1 through dP4 is equal to n by L, I am writing it for the time being, you will see why, okay, is all 0, right. So, I multiply this by 0, I eventually get 0 and multiply it by dP1, okay. Now, let us get the second column, which is interesting. So, to get the second column of kg, I will impose dP2. So, which is what I am showing here. So, I impose dP2. So, this node moves to that position, and now this is my displaced position of the bar. Okay. So, now let us consider the equilibrium of the bar in this displaced position. So, let us say this force is P1 plus D capital P1. This is P2 plus D capital P2. Similarly, this is P3 plus D capital P3, P4 plus D capital P4. Okay. And this change in the angle due to this d little p2 is d theta. Okay. And there is no change in the force in the bar. So, dF is equal to 0. That means, I still have n axial force, which is tension taken to be positive, right. So, now if I consider the equilibrium of this ith node in the deformed configuration, what do I get? I get dP1 is equal to 0 and dP2 is equal to that. How do I get that? Let me do it. So, let us say if I do summation fx is equal to 0, okay. So, then what I have P1 plus dP1, okay, in the x direction, plus n is the axial force, that means this force and its cos component, cos d theta is equal to 0, right. Now, this d theta is small, so cos d theta becomes unity, okay. So, I get P1 plus dP1 plus n is equal to 0, right. Now, what is my P1? Well, P1 is equal to minus n, because this is in equilibrium with the axial force n, right. So, that means these two will cancel and I get this one, dP1 is equal to 0, right. Now, let us consider the equilibrium in the vertical direction, Fy is equal to 0. So, if I do that, I get P2 plus dP2 minus n sin d theta is equal to 0, okay. Now, initially to begin with, I had P2 is equal to 0. So, this is gone, this is 0, okay. So, I get dP2 is equal to n sin d theta, right. Now, what is sin d theta? Well, this is the angle d theta, this length of the member is L. So, what is sin d theta? Sin d theta I can write is equal to n times dP2 divided by L, okay. Or this length is also L, right. So, that means sin d theta is equal to n into dP2 by L. So, that means from here dP2 is this quantity n by L times d little p2, okay. Similarly, if you consider the equilibrium of this joint, then what you would get? You would get dP3 is equal to 0 and dP4 is equal to that, right. So, now if I write them vector form, so d capital P1 through d capital P4 is n by L times this vector 0, 1, 0, minus 1 dP2, right. So, you can see that because of considering the equilibrium in the deformed configuration, we get some forces, that is dP2 and dP4, which is n by L and this is n minus n by L, okay, times of course dP2. So, similarly, if you apply dP3 is equal to some non-zero value and then all other displacements are 0, then you can get this expression, which is going to be all 0, dp3 0 means I am going to apply some axial extension to this. Okay. So, it will not offer any resistance, no change in the element and forces. So, that is equal to 0. And then I apply dp4. So, that means the bar is going to look like that. I consider the equilibrium, then I will be getting that. Okay. So, if I now combine all the equations, so then I get dp1 through dp4. So, these are my element and forces, or change in element and forces is equal to n by L, and then these are the vectors that I determined multiplied by d little p1 through d little p4. Okay. So, what is this? This is the change in end force, a matrix, times the change in element and displacement. So, this is my stiffness matrix, and this is called the geometric stiffness matrix Kg, right. And observe that this and this are all 0, and this is the same geometric stiffness matrix we have derived earlier by ignoring the axial extension dux dx on the geometric stiffness matrix. Okay. So, the non-zero first row and third row as well as first column and third column can also be derived using this, but then you have to use the principle of virtual work, virtual displacement to get the equilibrium equation, right. So, at least from this you understand what is the meaning of this entries, this non-zero entries in the geometric stiffness matrix. Okay. So, now let us talk about the geometric stiffness matrix for a beam column element. Okay. So, if you recall from the direct stiffness method lecture that we have a beam column element in local coordinate system. So, again little p's are the displacement and capital P's are the forces. So, we have 3 degrees of freedom at node I. So, P1, P2, P3, P3 is the rotation, and here P4, P5 and P6. Okay. So, we have already seen that when the axis of the element rotates and stretches, right. So, there is a rotation, okay, rigid body rotation and stretching, because of which we have already derived the geometric stiffness matrix, and that is for the truss element, right. Now, what additional thing we need to consider now for the beam column element? Well, we have to consider the effect of this rotation, right. So, that is what I am showing, that the element, let us say ij moves to I prime j prime, or the axis of the element moves to I prime j prime, and then there is flexural deformation like that. So, what we have to consider is the effect of this flexural deformation on the geometric stiffness matrix. Okay. So, to do that, what we have to do, we have to add the strain due to flexure, right, to include its effect on the geometric stiffness. Now, this is the case of pure bending, which we have already looked at in a previous lecture. Okay. So, you remember from there that the axial strain is equal to minus y into phi. What is y? Y is this distance from the neutral axis, and phi is the curvature, which is equal to 1 by rho. Okay. So, this I can write minus y d2 uy dx2. What is uy? Uy is the displacement in this direction. Okay. Just like if you recall in the previous case, so here this is the uy displacement in the y direction at some point which is at a distance x from the ith node. Okay. So, we can write the normal strain by neglecting the effect of rotation and stretching of element axis, because those things we have already considered for the truss element, or we have already considered that in here, right. Now, I am just trying to take care of this effect. Okay. So, epsilon x is minus y into phi, which is that quantity, and sigma x is E into epsilon x, which is this quantity, right. Now, I will not go through the entire derivation because it is slightly mathematically involved, okay, but you remember that the finite strain that you have defined in the previous class is this when you are considering a truss element, okay, where this is the first order strain and this is coming due to the rigid body rotation. Okay. And this is the new term that gets added, minus y d2 uy dx2, which is basically that term, right. So, now what we have to do? Well, we can derive from this using the principle of virtual work, virtual displacement, the linear elastic and geometric stiffness matrix, and we have to use the shape function like we did earlier for truss element. So, the shape function for ux is going to be the same linear shape function as we have derived or as we have used earlier, and for uy we will be using a cubic shape function for the transverse displacement, right. So, for complete derivation you can look at chapter 9 of this book. Okay. So, if you do that, then what you get? You will get the elastic stiffness matrix Kp, which is in local coordinate, and this is identical to that we have derived in the direct stiffness method lecture in lecture number 4. And you will get the geometric stiffness matrix, which is this. Again, it is a function of the axial force N, the length of the element L. Nothing else is coming into picture. And this is 6 cross 6 because we have got 6 degrees of freedom, 3 at each element N. Okay. So, if you are interested, I mean you can get in touch with me, I will show you the complete derivation. Okay. Now, with that, let us see how we can use the geometric stiffness matrices that we have derived to perform second order simplified P delta analysis. So, before I solve some example, let us go through the procedure, although you need not implement this because eventually you will be using a computer program such as OpenSys, but it is a good idea to know the procedure. So, the first step is form the global stiffness matrix in the undeformed configuration. Okay. So, it may include the geometric stiffness matrix for the entire structure if you have initial stresses, otherwise it is not essential to start with. Okay. So, use K0, so that is the first order stiffness. Okay. And if you use this, when you perform the iteration, as I will show in just a little bit, you need to do several iterations. Okay. If we use the tangent stiffness Kt, which is K0 plus Kg, remember when I use uppercase, this means the stiffness matrix is for the structure level, okay, and lowercase is for the element level. Okay. So, if we use Kt, then we need to do fewer iteration, typically 2. So, what we have to do? We calculate the incremental displacement by solving this equation, although I am writing Kt inverse Ru, but it is basically solved. It is not done like this, that in matrix inverse times this Ru. Okay. So, you determine delta R and then you update the displacement. Remember what is R? R is the structure level degrees of freedom or the displacement. So, now new updated R is previous R plus delta R. Okay. So, once I know the displacement at the structure level, I can extract the displacement for each element in global coordinates and which we call little q. So, once we get little q, I can get the deformation for each element using this transformation matrix AVQ. Okay. Go back to the direct stiffness method lecture, you will see that we have done V is equal to AVQ times Q. And here the compatibility is linear, or the relationship between V and R or V and Q is basically linear. So, what is the difference between Q and R? Well, R is basically containing all the degrees of freedom at the structure level and Q is in global coordinates for a particular element, right. So, AVQ is a linear transformation matrix because we are not talking about nonlinear compatibility yet. Okay. So, then once V is determined, what you do? You perform a state determination. If you have linear elastic element, then simply element stiffness matrix times the V. Okay. Or if you have nonlinear element, then for that given V, you perform a state determination to get the S vector. Okay. So, if it is nonlinear beam column element, nonlinear truss element, you can do this state determination, which is not this, but you have to do a state determination. Okay. Once S is determined, then what we have to do? We have to get the structure level internal forces. So, from S we will get the element end forces in global coordinates. So, which is AVQ transpose S. So, going from deformation coordinates V to Q, the global coordinates, right. So, this is my first order internal force vector Ri, okay, for one element, and then of course, I am summing it for all the elements. And then you have the geometric stiffness matrix which is in local coordinates, right. So, geometric stiffness matrix, if I do APQ transpose Kg APQ, then this gives me the geometric stiffness matrix in the global coordinates. So, in other words, I can write this entire thing is capital Kg multiplied by the Q vector for an element gives me the P delta correction forces or the second order forces, right, P delta correction terms. So, this total assembled for all the elements gives me the internal resisting force vector R superscript I. So, now what you have to do? Well, this external force vector that is not shown here, but you know from before that external force vector will naturally not be in equilibrium with Ri. So, Re minus Ri is my unbalanced force vector. Okay. So, what you do? You check for the convergence using the criteria that we have discussed earlier, okay, in the introduction chapter, right. So, if the convergence criteria is not satisfied, then you go to step 2, calculate new incremental displacement and then repeat the step. Okay. So, we can do this iteration using K0, that is the first order initial elastic stiffness matrix, or the tangent stiffness matrix considering the geometric stiffness matrix, and I will show you that this will require lot more number of iterations, whereas this will require fewer iterations, typically 2 iterations. Okay. So, with that, to get a feel for this procedure, let us solve some example by hand calculation. So, here I have taken a very simple example. Okay. So, this is a truss element and this is also another truss element, right. So, this area is AB, material Young's modulus is E, this is AC and E, this length is H, this length is L, this is subjected to axial force P and a horizontal load H is alpha times P. And this is my structural level degree of freedom R1 and R2. Remember, we are talking about truss elements. So, at each node we have got only 2 degrees of freedom. So, at this node we have got R1 and R2 and these DOFs are all restrained. Okay. So, perform a second order P delta analysis to determine R1 and R2 using an initial elastic stiffness iteration and using a tangent stiffness iteration. So, we will see the examples in SMaths Studio. So, this example file is already shared with you. Okay. So, the numbers that I have taken are here written here. Unit I am considering kilonewton and meter. So, this is AB, length of the beam is 2. I should not call it beam, but because I am using a truss element. So, length of the horizontal member is 2, length of the vertical member is 10. Okay. So, AC is 5 into 10 to the power minus 5, E is 2 into 10 to the power 8, P I am applying 20 kilonewton and alpha is 0.05. So, that means H will become 1 kilonewton. Okay. So, I will also share a first order analysis of this. If you do a first order analysis, what will happen? You will see that the force in this is equal to H, that is 1 kilonewton, force in this is equal to 20 kilonewton, as simple as that, because you are pulling it by 1 kilonewton force here and applying a 20 kilonewton downward force here. So, this for equilibrium in the undeformed configuration, this will have axial compressive force of 20 kN, this will have axial tensile force of 1 kN for first order analysis. Okay. That I am not going to discuss, because you already know how to do that using the concept of direct stiffness method that we have studied at the beginning of this course. Okay. So, now for element 1 I am saving the cross sectional area, length and the angle in this variable A, L and theta, and I am also calculating A by L just to get a sense what is the axial stiffness. So, that is 10 kilonewton per meter. Okay. And for element 2 similarly A2, L2 and theta is pi by 2, because this is vertical. So, the local x axis if I write, this is the local y axis. So, it is rotated, okay, by 90 degree. So, this is pi by 2 and this is the A by L for the vertical member. Okay. Now, the AVP, the transformation matrix for deformation from P to V is this, which we have studied in the direct stiffness method, and this is the force transformation matrix. Again, all these are covered in the direct stiffness method. Okay. So APQ is BQP transpose, and I can calculate the displacement transformation matrix from global to deformation AVQ, which is AVP into APQ. And if you do the multiplication, you get that, okay, where theta is the angle. And I can calculate the global stiffness for each element. So I is for element 1 and 2, AVQ transpose KV AVQ, okay. So this is for element 1, this is for element 2, right. And you need to now assemble the two stiffness matrices considering the 2 degrees of freedom R1 and R2. So these are my DOFs at the structure level. So we'll get a 2 by 2 stiffness matrix as we have done in the direct stiffness method. So this is my stiffness matrix, okay. Now we have to do the iteration. So vector of fixed end forces is equal to 0, 0, there is nothing, and the external force vector is 1 and minus 20. 20 is going downward, hence it is negative. So what is my unbalance? External minus R0, so which is 1 minus 20. So the incremental displacement is K inverse RU, which is this. So the current displacement, previously I had no displacement, so current displacement is this incremental displacement, which is 0.1 in the x direction, R1 degree of freedom, and minus 0.02 in the vertically downward direction, right. So now once I have determined this R, I can get the element and displacement for element 1, which is 0, 0, R1, R2, and similarly for element 2, okay. So once I get Q's for the 2 elements, okay, so what I am going to do? I am going to do AVQ times Q. So this is the deformation for element 1 multiplied by KV gives me the force in the element 1, okay. So that is equal to unity, right. And similarly for element 2, which is minus 20. Now for some reason it gives me in kind of an array form, which was giving me some problem. So therefore I saved it in S and then took the first entry so that it becomes a scalar, okay. So this is 1 and minus 20, right. So once S is determined, okay, so I can now determine the geometric stiffness matrix. So remember, in this case only element 2 is subjected to compressive force. So we'll consider the geometric stiffness matrix for element 2. So this stiffness matrix is geometric stiffness matrix will not lead to anything, okay. So let's not worry about that because it is tensile, right. Now, so this is the geometric stiffness matrix. This is the force which is minus 20, okay, and this is the stiffness matrix that we have derived. Now remember, this is considering everything and this is neglecting the effect of dux dx on the kg, right. So therefore the first and third row and first and third columns are 0. So this is my kg. Now what is the internal resisting force vector? So AVQ transpose S1 will give me the internal resisting force vector for each element. So this is for element 1, okay. Now for element 2 I can do this, but that is my first order force, right. But then I have to add the force due to geometric stiffness matrix, okay. So APQ transpose KG APQ will give me the geometric stiffness matrix for element 2 in global coordinates multiplied by the Q of the element 2. So this is my second order or P delta correction terms in the internal resisting force, right. So I have Ri for element 1, Ri for element 2. Now I need to assemble them to get the structure level Ri using the degrees of freedom mapping. So this is, if I go back just for convenience, let me write it. So this is the x direction, and for this element local x is like this, local y is like that. So that means for element 1 my global degrees of freedoms are like this. This is 1, 2, 3 and 4. Similarly for this element, okay, this is 1, 2, 3 and 4, right. So when I combine the internal resisting force vector for the R1 direction, I will be adding 3 component and this 3 component. For the vertical direction, this is 4th component and the 4th component. So that is exactly what I am doing here. Third component for element 1 plus third component of element 2. So that means this one plus that one. Similarly, the fourth component. Okay. So, this gives me the internal resisting force vector. So, what was my applied force vector? Applied force vector, if you recall, it was 1 minus 20. Now, what we got? 0.8 minus 20. So, that means the unbalance is Re minus Ri is that. Okay. So, we have to iterate to bring this unbalance down to an acceptably small value. Okay. So, I calculate new incremental displacement K inverse Ru. So, this is that Ru. So, this is my new incremental displacement, add it with the previous. So, this is the new displacement, and then again I calculate Q for element 1 and element 2 by extracting the displacement from the R vector, okay, and then calculate the basic force or calculate the force in the basic coordinates, okay, or deformation coordinates S1 and S2 for the two elements, right, and then again from the geometric stiffness matrix for the second element, calculate the internal resisting forces for both elements, basically repeat the same procedure, calculate the new Ri, okay, and you see that the unbalance has now reduced 0.04 and 0. In the first iteration or at the end of the first iteration, it was 0.2 and 0. Okay. So, we do one more iteration by taking this as the new unbalance. So, then these are my current displacement vector, okay, or the current displacements, and I repeat the same procedure. So, if we do that at the end of the third iteration, this is your unbalanced force vector, okay, and you do one more iteration and this is the final answer. You will see that the unbalance is equal to 0. So, it took us 4 iterations to get the final solution, right. Now, if I do the tangent stiffness iteration, okay, then you will see it will converge faster, okay. So, the initial procedure remains the same, everything is the same, okay. So, up to this point everything is the same, no change. In fact, the first iteration is also the same because I do not know what is the axial force in the element 2. So, therefore, there is no geometric stiffness matrix, right. So, I will be using this stiffness matrix. So, this is my external force vector, this is the unbalance. So, I calculate this is my displacement vector. So, same as the previous example with K0 or initial stiffness iteration. Okay. Now, so up to this is all fine. This is the Ru, the unbalance, basically same as in the previous example. Now, what I will do, I will form the geometric stiffness matrix for the element 2 in global coordinates. So, APQ, KG, APQ. So, this is the geometric stiffness matrix for element 2. So, what is my total stiffness matrix? This is the elastic stiffness matrix plus the contribution of this element geometric stiffness matrix considering the degrees of freedom appropriately. So, therefore, I am saying this will be 3, 3, 3, 4, 4, 3 and 4, 4. If you do that, then this is your tangent stiffness matrix considering the geometric stiffness of the element 2. Okay. So, now using this tangent stiffness matrix, if I do the iteration, so this is stored in KT. Okay. So, if I now do KT inverse Ru, okay, and you can see these are my final results. Okay. I got it in one iteration right after using KT, or total number of iterations is equal to 2. So, calculate the internal forces and eventually you find that the unbalance is equal to 0. Okay. So, if you use the tangent stiffness iteration. So, these files are shared both SMath as well as the PDF version, feel free to go through them carefully. Okay. Pictorially, if I show you, if I plot only the internal force in the DOF1 and the corresponding displacement R1 for initial stiffness iteration. So, basically this is K0 in scalar form because I am plotting only one DOF here. So, this is the applied horizontal load unity. So, you go like that, right, but your internal resisting force is here. So, this is your unbalance, right. So, you try to drive this unbalance to 0. So, you draw another line parallel to that, okay, that brings you here, and then again this is your internal resisting force vector considering the P delta correction term. Okay. So, you continue like so in a couple of iterations, as you have seen, we will get the final solution which is 0.125 okay, meter, right. So, here I am showing up to 0.12, and on the right hand side it is the tangent stiffness iteration. So, initially this K0 was 10. Okay. So, you go like that, and this is the unbalanced, right. Now, here your tangent stiffness is reduced, which is 8. How do I get 8? Let me show it to you. So, this 8 is this quantity here, and what is 10? 10 is the initial number. 10 is this number. Okay. So, you get to the solution directly, right. Now, in reality, what we often do, we apply the gravity load on our structural model first. Okay. Once we apply the gravity load and perform an analysis, then my geometric stiffness matrix can be formed, because all the members are now loaded and they have their axial force. So, then what we do, we apply the wind or earthquake forces, the lateral forces, and then we perform the analysis. So, in that case, there is no iteration necessary if your structure is behaving linear or the material behavior is linear elastic. Okay. So, that is what I am showing here. Again, Ri1 versus R1. So, this is, I have applied 1, okay, horizontal force. So, this is your initial elastic stiffness 10, but the moment I have applied the load, okay, considering the geometric stiffness, the lateral stiffness has become 8. So, that means this has reduced by the geometric stiffness minus 2. So, you will directly go to the solution and you will get 0.125 using a two-stage analysis procedure. Okay. So, let me show you that in OpenSeas quickly. So, here is the analysis file, very similar to what we have seen in the introductory lecture. Okay. If I do a first order analysis, like I said, this force will be equal to H, but if I do a second order P delta analysis, this force will increase, right. And to do that, what we have to do, so let me say this is the S. So, this all you can go through. So, this element 2 is an elastic beam column element, and the transformation tag here is P delta. So, this is what you have to state. You have to say to OpenSeas that please consider P delta geometric stiffness matrix. Note that in OpenSeas, the truss element does not have any geometric stiffness matrix, okay, but the elastic beam column has two transformation, linear and P delta. So, linear means it is first order stiffness matrix, there is no geometric stiffness matrix, but the moment you say transformation tag P delta, then it will consider the geometric stiffness matrix of that of a beam column element that we have derived. Okay. So, now if you go through this example, you will see that the horizontal displacement is 0.12499 and so on. So, that means it is 0.125, and that is what we have also calculated manually using the example we have just gone through. Okay. So, the solution is matching. Okay. And the internal force is 1.2 axial force, it is actually 1.25. If you go to the example, you will see what we have done a few minutes back here. The exact force is 1.25. Okay, but OpenSeas is giving you 1.2 because this graphical or the GUI program that is used, it is not showing you more than 1 decimal place. Okay. So, please go through this example. Okay. So, with that, let me summarize what we have done in this lecture. We have talked about geometric stiffness matrix for truss and beam column elements, okay, and we have done a physically meaningful derivation for the truss element and have given you the geometric stiffness matrix for the beam column element, did not go through the entire derivation. And then we have seen how to perform a second order analysis or second order P delta analysis, not large displacement, because we are considering only equilibrium in the deformed configuration. For compatibility, displacements are still assumed to be vanishingly small, hence VR or VQ relationships are linear. Okay. And we have also done a numerical example by hand calculation as well as using OpenSeas. In the next lecture, we will talk about the P delta, P big delta versus P small delta contribution, and then we will see lateral load behavior of frames. So, these are the references that I have used in this lecture. With that, thank you and see you in the next lecture.